Our new unit is about differential equations and slope fields. Today and the next lesson will be on differential equations, and then we'll shift into slope fields. First, what is a differential equation? And sometimes you'll hear the type that we're going to talk about is first order separable differential equations. A differential equation is simply an equation that has a derivative in it. When we call them first order, what that means is you're going to be dealing only with first derivatives. And when we say separable, what that means is we'll be able to separate out our two variables. In the next section, I've got steps laid out for finding a solution to a separable differential equation. And without going into too much detail, basically what we have to do is separate the variables. Then we're going to do two antiderivatives. That plus c is going to be written only once. If we're given an initial condition, we're going to plug it in and solve for that c. Then we're going to plug that c back into our differential equation and then solve for y. And then there's a way that you can check your answer with your initial condition. So let's just jump in and do one. So our first example here, and pay special attention to the directions, because sometimes it's easy to do the wrong thing at the wrong time. So definitely tie this directive into this process that we're getting ready to do. So it says find the particular solution, y equals f of x, to the differential equation with the given initial condition. So this is my differential equation. My derivative is sitting right here. My initial condition says when I plug x equals 1 in, I get 3 as my answer. So this here is my x, and this here is my y. And really what these directions are telling me to do is find the function y whose derivative is x over y. So I'm looking for a function y that when I do its derivative, I get x over y as my answer. And I'm just going to follow that process laid out above. Step number 1 is to separate the variables. Put the y dy on one side and the x dx on the other side. To do that, I think a first good step is just to get that dx out of the denominator. So multiply both sides by dx. When I do that, it looks like this. One of the requirements was that the dx and the dy, they're called differentials, they are not allowed to be in that denominator. So by multiplying by dx is your first step. You're putting it in a position that it needs to be in. And then take a look and see who is out of place. And remember, we're just trying to separate the y's on one side of the equals and the x's on the other side. So it's this y here. To get it to move to the other side, I'm going to multiply by it. At this point, I've accomplished step number 1, which was to separate the variables. Step number 2 says to find the antiderivatives of each side. My antiderivatives are both just power rules, so add 1 to the power, divide by the new power. Technically, each antiderivative generates its own constant of integration, but what I've done is I've combined both of them because you're going to get a plus c on the left for that antiderivative and a plus c on the right. But just think of it as I'm taking two arbitrary constants and combining them into one. It's convenient to write it on the side with the x because one of the steps later on is going to be to solve for y, so that'll just save me a little bit. If you're given an initial condition, and I am, my next step is to use that initial condition to find c. So I'm going to pull off to the side and plug in x equals 1, y equals 3, and then solve for c. When I do that, I get a c value of 4, so I come back to my equation and I'm going to replace the c with the 4. We have just finished step number 4. For step number 5, I'm going to take this equation and I'm going to solve it for y. Multiplying by 2 on both sides gives me y squared equals x squared plus 8. And my next move is to take the square root of both sides, and I must take the plus or minus square root. So now what I have to do is make a choice. The answer is either the positive or the negative square root of x squared plus 8. What determines which of these is the answer is the one that works with my initial condition of y of 1 equals 3. And when I plug my x equals 1 into this, I get a square root of 9. And it's either plus or minus 3, but because I want the y to equal a positive 3, I'm going to choose the positive square root as my answer. And so my answer, my solution to the differential equation is y equals the square root of x squared plus 8. Remember what we said initially? We said we were looking for a function in terms of x that when I did its derivative, I end up with x over y. So what that means is I should be able to take my answer, do a derivative, and end up with x over y. So I'm going to go ahead off to the side and do a check of this. The check I'm doing over here is optional. So I first rewrite my square root as a 1/2 power. Now I'm going to use a power rule and a chain rule. Here's my derivative of the outside is to bring down the power and subtract 1 from the power. Leave the inside alone, so the x squared plus 8 times derivative of the inside. Keep in mind, I'm trying to get it to equal x over y, so I'm going to manipulate this a little bit, starting with this power. So the negative 1/2 means I can take that x squared plus 8 and write it in the denominator with the 2. Let's simplify a little more by canceling out those 2's. And what I have here, the x squared plus 8 to the 1/2 power, is exactly how y was defined, which means I can replace that with a y. And after I simplify it, I get dy dx equals x over y, and that's exactly what I started with, which tells me my answer looks good. Let's go ahead and take a look at another one. Ooh, everybody's favorite, a trig function. All right, in example number 2, I have dy dx equals cosine x over y squared. So start off by multiplying both sides by dx. And then I take a look at that, and I see that y squared is out of place, so I'm going to multiply both sides by y squared. I've achieved my separation. Next comes my antiderivatives. The antiderivative of y squared is y cubed over 3. Antiderivative of cosine x dx is sine x. I write the plus c on the side with the x. My next move is to use my initial condition, plugging in x equals pi and y equals 1, and solving gives me a c value of 1/3. So I come back to my equation and I replace the c with the 1/3. Next comes solving for y. I'm going to multiply both sides by 3 and then take a cube root. One thing to notice here after I solve for y is I didn't put a plus or minus on this because that's a cube root. You only use a plus or minus if you have an even root. So here is my answer. Let's go ahead and give it a check like we did on the other one. So I'm going to take the derivative of the cube root of 3 sine x plus 1. That derivative is going to start off with the chain rule. Remember, what I'm trying to do is get this derivative to say the original problem, which is cosine x over y squared. And so far it looks nothing like that, so I'm going to have to clean it up a little bit. I see that these 3's are going to cross off, and I'm going to handle this negative 2/3 power by putting it down in the denominator. I'm going to rewrite things in such a way that will help me get back to that original problem. So this negative 2/3 power became positive when I put it down here in the denominator, and I pulled the 2 outside of the brackets and left this as a 1/3 because I'm trying to match up with this. So now everything that's sitting here in the brackets is exactly what y is up here, which means I can replace it with a y. And once I do that, it's like a little math magic. I end up with what that original problem was, which means my answer here is a good answer. Let's go ahead and take a look at another example. All right, so our third example is going to start just like the other ones did. I'm going to start by multiplying by dx on both sides of that equation. And then I look and I see that my y is on the wrong side, so I'm going to divide by it to move it to the y side. So at this moment, I've achieved my separation. Next comes my antiderivatives, and this looks like it's going to be a natural log over here, and then a power rule on the right side. Next, I'm going to go off to the side and use my initial condition, which is x equals 0 and y equals 2. That gives me a c value of the natural log of 2. Generally, these are without a calculator, so you're just going to leave it natural log of 2 and replace the c with that. My next step is to solve for y, and sometimes that's easier said than done. I'm doing the natural log of y over here. So what's going to remove that natural log from the y is to exponentiate both sides. So each one of these will become the power of e. Over here on the left side, exponentiating and natural logging are inverses, so they are just going to wipe each other out. It's going to leave that absolute value of y. And over here on the right side, if I want to give each term in the exponent its own base of e, I actually separate it with a multiplication sign. You're used to seeing this property go the other way. When we have the same base and we're multiplying, we add these exponents together. I'm just working this in reverse. What that allows me to do is change this over here is just equal to 2, and then I just wrote that 2 in front right here. The next thing I have to do is clear this absolute value right here. So recall that when you have an absolute value equation, as I do right here, I can split it into two equations. One would be the positive 2e to the 2x squared, and the other one would be the negative 2e to the 2x squared. And my one absolute value equation has become two regular equations. So I have y equals 2e to the 2x squared and y equals negative 2e to the 2x squared. So now I have to choose which one of these I want as my solution. What's going to drive my choice is that initial condition. My initial condition said when x equals 0, I want the y to equal 2. If I try that in this one over here that has the negative 2, if I put a 0 in for that x and square it, I get e to the 0, which is 1, times a negative 2. I would be looking for a y value of negative 2, yet my initial condition says positive 2. What that tells me is this one is not the answer. If I plug my x equals 0 into this one, I get e to the 0, which is 1 times 2, and I truly get a positive 2. So that makes this one, the y equals 2e to the 2x squared, my answer. Let's go ahead and check it like we did the other ones by finding the derivative. Doing a derivative of an exponential, I start by writing down the exponential exactly as I see it, and then I multiply times the derivative of the exponent, which gives me a 4x. And then this part here, the 2e to the 2x squared, is an exact match up here, which means I can replace that with a y, and I get dy dx equals 4xy, and that was my original problem, which means my answer looks pretty good. Our last example here is actually a review problem, but it uses a lot of the terminology of this section of a differential equation and a particular solution, an initial condition, so I went ahead and included it. But really what it wants you to do is just write the equation of a tangent line. And you know, in order to write an equation of a tangent line, we need to know two things. We need a point, which we have, and we need a slope, and that's what a derivative gives us. And once I have my point of 1, 1, and my slope of 5, I write my tangent line equation. Then it's asking me to use this tangent line equation to approximate f of 1.1. So this goes back to that linear approximations that we had done previously. And plugging my 1.1 into my tangent line equation and then doing those calculations gives me that linear approximation of 1.5.